So in fact, we have written a roadmap for AI for Science, and still in progress, but we have the first version out. So what we have been doing is to outline all the scientific use cases for AI and combining AI with simulation. It's a 150-page addition to our computing science roadmap. Unfortunately, it's in Japanese right now, but it's being translated, hopefully soon. But no, this is only beginning, okay? So we want to really, not only to showcase what we have today, but we want the outlook for the next 5-10 years, because we'll be developing machines 5-10 years out. So we want this perspective of what scientific problems we might be able to solve using AI and science and simulation. Also doing projection on the performance projections. And this says, right now, it says, well, we need at least a few hundred exaflops to do effective training of very large models for science. And this is our target. And this is our target currently, but I'll get to that later. Okay? So RIKEN's flagship AI project is called TRIP Aegis. And TRIP is like transforming science with computing. And so it's not just our center, but multiple centers within RIKEN is involved. So like I mentioned, we want to automate the process. This particular project, we want to automate the process of science by having AI generate from the hypotheses and the experimental plans. We want it, we may run the experiments with robots, or we may use simulation and get the feedback the results on this PDCA cycle. There are various domains we're looking at, like foundation models. So we're taking more of an approach of individual scientific foundation model for each domain. So we're trying to get, we're trying to compare that with the approach that Argonne is taking, having one big model, whereas we're trying to create smaller models, but of course we're working with them to see how they compare, okay? Because right now, that's because we don't know. They don't know. It's important to compare. So we're trying to create foundation models of cellular response, foundation models for animal behavior, because we have tens of thousands of mouse cages in RIKEN. So it's very important for our people who work with lab mice to have foundation models for that. For farms, for drug development, also foundation models for certain various types of material science. Just to give you an example of some of the challenges of work being done by Mohammed Wahib, along with our colleagues at Oak Ridge and others. So what they want to do is to have a foundational model to handle these very, 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 very high-resolution medical images, like 100,000 by 100,000, instead of your typical iPhone with or internet images like 1,000 by 1,000. So this is 10,000 times higher resolution. Okay, so terabytes. Each of these images can be terabytes. If it's in 3D, this is 2D, but in 3D it can be like 100 terabytes per image. Okay? Per image. So, but we want the foundation models. We want the multimodal foundation models to handle this. And I can tell you there are no foundation models that can handle this currently. Because in order to feed us images like that into foundation models, the typical strategy to take is to subdivide these into to these little patches as tokens, and you would feed these tokens. But unfortunately, if we have 100,000 image, the sequence becomes just too long. So there are no models that can handle this. So on one hand, we're working on to prolong the sequence that can be handled that can handle these types of extremely long sequences, but also we need to compress the sequence length. So then we're taking one approach they're taking is to use what we're familiar with in HPC simulations is to use quad-tree-like compression technique, by which we subdivide the area not into equal segments, but rather into these rectilinear segments, square segments, but subdivided. depending on the resolution like that. And then you have a space filling curve, like the Z curve or Morton ordering, or like Hilbert curve. And you have so you linearize sequence. Again, this is a technique that typically used in simulation, but we use the same technique to generate sequences out of this quad-tree structure. And this particular example, this is a small example, you get like, you shorten the sequence length by an order of magnitude. And you can even do that even more for high resolution images. Okay? So these are some of the not only combining simulation and HPC, but taking a lot of techniques that have developed in HPC and applying it to AI, rather than having a very simplistic approach that typical AI scientists are taking. Okay? And a technique like this is very useful because, okay, that was a stuff being applied to medical images for cancer treatment, cancer diagnosis. But this is similar work now being done in collaboration with the brain scientists to basically essentially trying to replicate brains in digital space. So you do a non-intrusive scan. So there are a group of people at Duke University. Now they can do a 5-micron resolution scan of human brain, non-destructive scan of human brains. Okay, so that's great. Then you can go into like neuromorphic connections of the brain. And at RIKEN, we have a technology to simulate the entire brain. We can do full human brain simulation on Fugaku now. The problem was we didn't have the program. Okay, but these Duke University people now have the ability to generate the program, but they can't simulate it. So these will be mated to, and also there will be these the recognition techniques to reconstruct the connections. We'll also use foundation models. So combinations of all these technologies may allow the science fiction thing, in which it's called a conscious uploading, uploading your brain into digital space. Now, it may be possible with this new work. So we'll see what happens. I'm paying very close attention to this. Very interesting. We'll start with the mouse, by the way, not with humans. But, unfortunately, we don't quite have artificial intelligence to that level yet. Also, at the system level, we're working rigorously on many, many, many fronts, looking at these very high-end AI use cases. And also, we are, because Fugaku is already filled and also wasn't designed, not necessarily designed to accommodate AI. Well, it's a decent machine, but we need acceleration. So we're building a new machine to be tightly coupled with Fugaku to accelerate our AI capability. But this is a 2025 machine, and we'll do, this is not Fugaku Next. Fugaku Next is something different. And we'll also have signed various agreement with like the DOE, also the European centers, also some centers in Asia. But these are signing signatures are being now done at the government level. There's very high interest in co-developing these technologies on the high-end simulation and AI. Okay. A bit of a word on quantum, although I'm running out of time, so I'll be very brief. RIKEN has several centers working on quantum. The biggest center is RQC, and there are people, our collaborators, but they're the people building and actually designing and building a real quantum computer. Okay? So RIKEN has its own quantum computer called the A machine, A as an alphabet. But these are physicists trying to create their own unique quantum computer. Whereas we, as a supercomputing center, we are all working more on the facility and software and algorithm side. And of course, we're in collaboration. So our new project is basically trying to create a platform where this error-correcting quantum computer happens, and our exascale or even zettascale machine in the future happens, combination of which, with appropriate software algorithms, will make quantum computing be tangible for certain important areas like material science, for example. And so we're preparing a platform to basically make that happen once these happen. So, but we are building a real platform, so we are getting multiple numbers of real quantum computers, but also quantum simulators. So we'll get the real machine, also get the simulators, so working to advance our simulation technologies as well. Of course, we'll work on new machine, work on like error mitigation and all that. And of course, we have the classical side, we have Fugaku, and also we'll facilitate the GPU machine. So a combination of which we are building a software platform to allow for very ease of use, and also algorithms and applications to prepare ourselves in, let's say, around 2030, when quantum computing for certain areas, in combination with traditional HPC, becomes a reality. So this is one of the machines that will come on our floor in 2025. This is the IBM Heron. It's 133 qubit. You may see this during the tour. Of course, the machine's not here yet, unfortunately, but you'll see the floor space where this will be installed. It's a big lot. Yeah, but we'll come back in about a year. You'll see the real stuff. We'll also have simulators again. We have a simulator work on Fugaku. We also have a simulator work on a GPU machine. Also have other real quantum computers, including the A machine, also the ion trap machine by Quantinuum, and also working with other quantum computer vendors to incorporate quantum machines. So it's quite a comprehensive platform. Very expensive, hundreds of millions of dollars, but it's worth it. So finally, we're working on Fugaku Next, our next generation, because supercomputers is like a work of art. You finish it, okay, you're done. You say, oh yeah, I've done my best. But then after a while, you look at, I could have done this better. Oh, there's a new technology. Oh, we're getting complaints from the users. This sucks. This part sucks. We got to improve this. Some of the improvements, of course, will be done by software and operations. But then there are certain things you can't change, right? So because it's in hardware, or you may add new stuff like the AI portion of Fugaku. But again, it's only addition. So there's always an endeavor. I've been doing this for like almost 30 years now, to build, design, and build a new machine. So this time, we are working. What's different from like KA Computer, the predecessor in Fugaku, is that we are working with major vendors internationally. Not just Japanese companies like Fujitsu, but also Intel, AMD, NVIDIA, Hewlett-Packard, also ARM, although we don't know which depending on who we ask, ARM might be a Japanese company, or US company, or British company, so we don't know. But we are working with all these companies, as well as all the other centers in terms of software and applications, and also operations. So it's more of an all-Japan team, plus a lot of our collaborators and vendors, also major institutions like the DOE labs. So we have a big joint project with the DOE, and also trying to establish that with Europeans. Some of the key observations, I can't go into details because a lot of these work is still under NDA, but I can give you a few hints. So one of the key research is to really investigate what the applications do. And we all know that most HPC applications are memory bound or bandwidth bound, but we have done various work to confirm this. So the key innovation moving forward for most applications for traditional simulation is to increase memory bandwidth. But also to have some heterogeneous architecture, and we don't have heterogeneous architecture for the sake of having heterogeneous architecture, but we'll have a heterogeneous architecture to classify, we classify the workload, and each of these workloads, once classified, we'll try to be generic as possible. Then we will be assigning the workload to architectures that will fit best. according to the characteristic workload. So memory bound, okay, we assign it to memory bound, well, basically a vector processor, like GPUs or CPUs with vectors, whereas things like AI will assign it to matrix engines. Okay, that's good, but what's the biggest challenge? The biggest challenge is energy, because we want to build machines within a reasonable budget. Like Fugaku is about 20 megawatts. In the center, you'll see, well, in total, we have a capacity of about 50 megawatts. Okay? But that's big. That's tens of millions of dollars of annual expenditure. Also, lots of CO2 emission. So we can't go, we can't be all liberal about power. But then, when we try to increase computing, for various reasons, we're hitting lots and lots of difficulties. Not like the past, but now we're hitting so many physical limitations. It's the biggest challenge. How big a challenge? Well, for example, in order to increase the performance of most of our codes, which are memory bound, fundamentally you have to increase the memory bandwidth by that appropriate amount. So if you want factor 10 speed up, you need to increase the memory bandwidth by a factor of 10. If you want to increase by 100, you need to increase by 100. But in order to hit our target, be more than an order of magnitude faster than Fugaku, we have the limiting factor will be the energy of transfer between memory and the processor. And when we really want to achieve the speed up we want to achieve, we have to go down to something like 0.2, 0.5, 1 picojoule to even below that, 0.2, 0.5 picojoules per bit. And to put this in context, the new chiplet standard, UCIe, just moving data from one edge of the chiplet to another chiplet under the spec is 0.2 picojoules. So no matter what we do, right, no matter what we do, we'll be bound by energy. And we need to innovate to bring our energy. And again, we're working on several things with our semiconductor friends. I can't tell you about it, but we have some innovative stuff that everybody wants, basically, not just us. All the GPU vendors want this. All the hyperscalers want this. Because, again, also AI is partly compute bound, but very much memory bound. So everybody wants the technology. And that's what we're developing right now. Yeah. So, of course, we have our architecture. And like I said, we need a few hundred exaflops at least. And the vendors are coming up with various plans with us. Yeah, so hopefully we can achieve that. Along with AI, advanced AI, achieve essentially the so-called zettascale performance for Fugaku Next in 29. That's our goal. Now, how to achieve our zettascale performance? Well, one way is to achieve it physically. We may be able to do that. Again, I can't tell you, but we might be able to. The other is to try to use techniques like surrogates. We believe by combining all of these, we are able to achieve zettascale in 29. Hopefully. Okay? That's our goal. If you're interested, you can work with us. Okay? And we have, I'm cooking all these plans, but yeah, which is something that we got to do. But hopefully, we can be a little bit open about this in about a year time. But in 25 April, hopefully we'll launch our Fugaku Next project. By that time, I can talk to you more about our zettascale plans for 29. Okay. With that, I'd like to end my talk. Thank you, and I got to run to the airport.